Professor Elizabeth Behrman is Professor of Physics and Mathematics at Wichita State University, Kansas, USA. She obtained her bachelor's degree in mathematics in 1979 from Brown University and master's degree in chemistry in 1981 from University of Illinois at Urbana-Champaign. She obtained her PhD in chemical physics from University of Illinois at Urbana-Champaign in 1985. She worked as a graduate research and training assistant at University of Illinois at Urbana-Champaign from 1979 to 85 and as a postdoctoral research associate at State University of New York at Stony Brook from 1985 to 86. She served as an assistant professor of ceramic engineering at New York State College of Ceramics at Alfred University from 1986 to 90. She joined Wichita State University as assistant professor of physics in 1990, became associate professor in 94, and a full professor in 2002. She is a professor of physics and mathematics at Wichita State University at present. She has done pioneering work on modeling of microtubules as quantum Hopfield networks and has published several papers in leading journals. She has won several research grants, including those from National Science Foundation, Optoelectronics Industry Development Association, Dwight D. Eisenhower Professional Development Program, and Center for Consciousness Studies, University of Arizona. All of us are eagerly waiting to hear the valedictory address of Professor Behrman entitled Quantum Neural Networks and the Problem of Consciousness. Professor Behrman, please.
Thank you very much. Thank you very much for the honor of giving this talk. I need also to thank my collaborator, Jim Steck, who worked with me on some of this work, and some of my students who also did some of the calculations. Kavita Gadam, who I believe is Indian, and Raheel Alodin, and Stuart Bomer, and Kathy Walsh. Okay, so this whole conference is about consciousness. What is consciousness? Well, we want to say that consciousness is the awareness of ourselves as that we exist, that we're aware of not only ourselves but also of our surroundings. And we think that this is something that humans certainly have, and we're convinced of it. I think animals have this to some extent, and we've heard some talks about this with respect to animals and even with respect to plants who have some of these things. Well, so this has been a problem that people have worried about for a very long time, as we've heard from many speakers throughout the conference. So the first question we need to ask is can consciousness be explained by science? And as scientists, of course, those of us who are scientists, we say, well, yes, everything can be explained by science. Of course, you know, that's just an article of faith. I mean, how do we really know that everything can be explained by science? It's always seemed magical to me, and perhaps to some of you, that we can understand the universe at all, that we can make mathematical models, predictive models of the universe, and that they actually work. Well, okay, so we don't actually know whether or not consciousness can be explained by science, or whether we need something outside science to explain this. And many religious people have said this. But I'm going to operate on the assumption that we can, because that's really what I do. So we're going to say yes, okay? But the rest of these questions, you know, how do we get these sensations? How do we get these, what philosophers call qualia? How do you get qualia out of the physical workings of the brain? That seems like a leap, okay? What physical mechanisms are responsible for these things? And most of all, perhaps to me anyway, on what scale or scales is or are the relevant physics? I mean, what's going on? So the rest of these things are really quite a puzzle. The systems that we need to investigate are complex, and they involve skills and knowledge maybe that we don't even have yet, but certainly that involve all of the disciplines we see represented here today. And this is why an organization or a center like the Center for Consciousness Studies is such an exciting thing that we've inaugurated here at this workshop, is that we bring together all these different experts in all these different fields. Well, I'm not an expert in most of your fields. In fact, I know almost nothing about most of your fields. And so today I'm going to talk to you about my own take on this particular subject, which is that of a theoretical or computational or mathematical physicist, and I hope you will all find it informing and interesting. The first half will be pedagogic, okay? So even those of you who are not theoretical physicists, I hope will get something of a flavor of what it is that my research means, and one particular, as I say, one particular take on this subject. Those of you who are experts in one or more of my fields, because I kind of span a couple of fields myself, I promise that that even though you may find the first part a little dull, although I'll try to liven it up, you'll find some new results that have not even been published yet if you'll just hang on for the second half. Okay, so I'm going to begin by talking about neural networks, okay? What are neural networks? Okay, well, neural networks are a different architecture for computing. Different from the machine that I see in front of me. Well, all right, this is an algorithmic computer. This has an extremely complex central processing unit. Yeah, I mean, we all know this, right? Well, a neural network, both artificial and natural, is organized on a different principle. Instead of one very complicated central processing unit, several people know this stuff, but instead of this, we have many, many very simple processing units that are multiply interconnected, okay? So this is just a schematic of one possible neural network. This is a feed-forward neural network for those of you who are interested in these things. And though the algorithmic computer is ubiquitous, I mean, obviously it's ubiquitous, and though it's been extremely successful at doing huge numbers of things in our modern society, with enormous numbers of applications, the neural network architecture is also hugely successful with no algorithm needed, and I'm going to point out why that's kind of important later on. The architecture constructs its own algorithm. Okay, so how does this happen? Well, it does this through something that the neural network community calls learning. And we call it learning because it's very much like what we ourselves do. So what happens? Okay, so here on the bottom, here we are. Here on the bottom we have the input layer. Here on the top we have the output layer. So how does learning take place? Well, we initialize the input layer in some sort of input state, okay? And then that information propagates through these multiple interconnections, through many perhaps hidden layers here, into the output state, and that's where the output is read, okay? So even though each of these neurons, we call them neurons in analogy with the things in our own brains, even though each of these neurons may have only a very simple processor, and the simplest one, of course, is the one in which each neuron sums up all the inputs that are fed into it with some kind of a weighting function, and then decides whether or not to fire, whether or not to turn itself on and send a signal outwards. So it's an extremely simple kind of processor, and yet these kinds of networks are capable of doing very complex calculations that we don't know how to program an algorithmic computer to do. And this is why they're so important. Well, that and the fact that they're analogous to our own brains. So how does the learning take place? Well, we initialize the input layer to each of a number of inputs. We then read the output, and it may not be the answer that we want. So we change the weights whereby each of the inputs is weighted and before it goes on to the next layer. We change them in such a way as to decrease the error. And there are systematic ways of doing this so that we're not just changing the error at random, but actually in a direction that will minimize the error. This is called steepest descent for those of you who are familiar with that idea. Anyway, after a number of passes through the set, which are in other words, we initialize it in the first set, we pass it through, we get an error, we change the weights, the second set, the third set, and so on. So after a number of passes through the training set, we have the set of weights here in the final state, and we say, okay, this network is now trained to do whatever it was that we wanted it to do. So what might we want it to do? Well, for example, for decades now, the phone company, and that used to be a singular term, at least in the United States, it just meant AT&T, has used neural networks for noise reduction. And when you think about it, it's actually a kind of a complicated and difficult problem. How do you decide what part of the signal is noise and what part is your grandmother's voice that you very much want to hear? So how do you decide this? And it's very easy for our brains to do this, or relatively easy. I mean, we can filter out the noise in a crowded room, and we can just concentrate on the one person that we're talking to. But that turns out to be a very difficult problem for an algorithmic computer. Another possibility, or another example, the Navy uses neural networks for sonar object recognition. Again, this is very much so as to mimic the biological system. What biological system? Well, of course, you all know probably that dolphins do this, okay? Dolphins send out signals I'm not exactly sure how, but they send out signals, and the signals, the sonar signals bounce back, and the dolphins read them somehow. And I'm at sea with this biologically, but I'm sure the biologists in the audience know exactly what I'm talking about. And somehow they interpret these signals, and they decide whether that object is a piece of food or a human being or a log or whatever the heck it is. So the Navy uses artificial neural networks to mimic what it is that dolphins do. This is kind of a gruesome picture here, but aircraft stability control, as aircraft have gotten more and more complicated, and the number and variety of the control surfaces have multiplied, it's become more and more a task for computers to guide aircraft, as you know. Well, what if, God forbid, something should happen to your control surfaces, as happened in this picture here? This is an aircraft wing that got hit by a missile, but it took some very clever piloting on the parts of the pilots, and it would be nice, and this is not an in-place system, but it would be nice if we had an in-place system that could control the aircraft in the event of such a situation. Then there's voice recognition. I mean, how do you know who it is on the phone? You can't see this person. I know immediately it's my mother. She doesn't sound like anybody else in the world to me. Okay, well, how do I do that? Well, I don't know exactly. I could not describe to you how I know that it's my mother. I just know. All right? Well, what do all these things have in common? They're all pattern recognition. Something that it's actually fairly difficult to teach an algorithmic computer how to do. How does an algorithmic computer know that the person walking down the street 100 yards away from you, 100 meters away from you, how does an algorithmic computer know who that is? Well, it could do pixel by pixel comparison, but what if the person is wearing a suit of clothes you've never seen before? What if they've changed their haircut or even colored their hair or something of that nature? Well, the algorithmic computer would compare pixel by pixel and say, we don't know this person. But I recognize immediately that it's my sister or whatever it is, okay? Why? How do I know that? It's the way she walks. It's just something about her, and I know instantly. Yeah? I mean, you all know this, right? So all of these are examples of pattern recognition, and this is really what we mean by the intuition that we were hearing about in earlier talks. What is intuition but pattern recognition? Okay? Maybe that's just another name for something that we already don't know what it is, but it turns out that artificial neural networks, which we human beings construct, are actually very good at pattern recognition. And we think that the power of the artificial neural network comes from the multiple interconnectivity of the processing units. Okay, that's where the complexity comes from. So the question is, for us today, and perhaps for decades to come, is consciousness a neural phenomenon? Okay, we've heard many times today, is consciousness a quantum mechanical phenomenon? And we're going to talk about that too, okay? But is it a neural phenomenon, okay? This is something that I want to answer as well. Okay, so your brain, possibly, okay? Well, your brain definitely, okay? Your brain is obviously a neural network. For one thing, you can see by these cartoons that it's a neural network, okay? A cartoon makes it something clear as nothing else does. Here are neurons and they're multiply interconnected. Doesn't that look like a neural network, not a multiple central processing unit? Of course it does. Which is, of course, the inspiration for artificial neural networks and why we built them in the first place. Okay, so clearly it's a neural network, and we know that because of the architecture. We know that because the way people are programmed. I mean, we don't just have a programming tape that we insert into a child's brain. I mean, this is not the way learning happens. The way learning happens is by the same process that I was describing earlier with the artificial neural network. I mean, we all know this, right? How do you know how to ride a bicycle? Well, you know how to ride a bicycle because you ran it through your neural network multiple times until you got it, right? Yes? Yeah, we all know this. Okay. So clearly the brain is a neural network. So we know this from the architecture. We know this from the programming. We also know this from the fact that the connectivity is plastic. And many people in the audience probably know this a lot better than I do. But of course, we all know that the connections between the neurons in the brain are not completely hardwired at birth. Okay? They're plastic. And in fact, if a baby does not hear certain sounds within a very short time after it's born, it will never be able to distinguish these sounds later on in life, which is why, well, I don't know very much about linguistics, and I'm sure people in the audience know a lot more than I do. But if certain connections are not reinforced immediately, they become lost. They are not there. They're not able to be plasticized or remade or whatever. There are other connections that remain plastic throughout life, which is a good thing because otherwise we couldn't learn anything, okay? And we're all learning so much at this conference, okay? So great stuff. So is consciousness a result of this plasticity, okay? So this remains a question. Second question, is consciousness quantum mechanical, okay? And here we have the famous Rodin statue, which of course most of you know. And for those of you who don't know, the thinker is thinking about the Schrodinger equation. Okay, so is consciousness quantum mechanical? All right, this is something that, although we're doing a lot of work on it here in this room, people here and people around the world, something we still don't know what the answer. And we have to say, well, of course, the interactions at a small enough length scale are quantum mechanical, subneuronic. And the electrical and chemical synapses of these, of course, they're quantum mechanical. The whole world is quantum mechanical. I mean, all the universe, as far as we know, is quantum mechanical. And we've got piles of evidence that the universe is quantum mechanical. I would be extremely surprised if we found out that quantum mechanics was wrong. It may have to be expanded in my daughter's time or my granddaughter's or something, but we're getting a lot of things right. And the fact that these machines all work is ample evidence, at least to me, that quantum mechanics is the basic theory of the universe that explains how the universe works. But the question is, on what level? Okay? The whole world is quantum mechanical, but this is on a device level. The question is, does this happen on a systems level? Right? For the past couple decades now, we've been trying to build quantum computers that are systems quantum computers, not just this machine, which is quantum mechanical. Of course, it's quantum mechanical because otherwise solid-state physics would not, allow that to work. But it works on, but it's only quantum mechanical on a device level, not a systems level. So we've built quantum computers, but they're very, very small quantum computers. Okay, just a few qubits. We're going to talk about that. Well, so. Is the brain quantum mechanical? And we might say, of course not, okay? We might say that sort of automatically. In fact, most of my colleagues would say, of course not. No offense to anybody here. And why would they say, of course not? They would say, of course not, because A, the scale, okay? The brain is large, okay? And we're used to having quantum mechanics only work on a very, very small scale. And I've been teaching quantum mechanics for decades, okay? And many of you have actually taken a quantum mechanics course. And you know this. I mean, the systems that we talk about that are quantum mechanical in our quantum mechanics courses, they're tiny, okay? A hydrogen atom, okay? A bond between two atoms, okay? Well, we'll talk about some of them later. So we think no because of scale. We also think no because of temperature, okay? We know, or we think we know, that quantum mechanical effects are destroyed by thermal effects, okay? And we'll talk about exactly how that happens a little bit later on in the talk. Let me just show you two examples of things that might give us pause in this of course not thing, a reaction that many of us have. And one of them, of course, is the buckyballs. Those are fairly large, okay? These bombs are, these guys are tens of nanometers across, and they exhibit quantum coherence, okay? There's also the squid, which is a macroscopic quantum mechanical device that exhibits coherence, quantum coherence on a macroscopic level. Okay, so what is quantum mechanics? What is it that I mean when I say, is this quantum mechanical? Well, what I mean is, well, four things, okay? First is something called wave-particle duality, and I'm sure you've all heard of that. Okay, famously, a quantum system is both a particle and a wave. Well, what the heck does that mean? All right. Superposition, that is, a quantum mechanical system can exist in two simultaneously exclusive states at the same time. There's also the phenomenon of entanglement, which comes from the phenomenon of superposition. Okay? And the entanglement is that marvelous property whereby if you've got two entangled subsystems, even though you have no idea what state either one is in before you measure, if you measure one of the subsystems, you instantaneously know the state of the other subsystem, even if they're very, very far spatially separated. And this is the phenomenon that makes it possible to do the quantum teleportation that we heard about in an earlier talk. Finally, there's this quantum collapse, the measurement problem. And we still don't know quite how to deal with that. Some people, of course, still hew to the Copenhagen line. Some people prefer the Leverett-Wheeler many worlds hypothesis. And I want to emphasize, though, that Copenhagen and Leverett-Wheeler both give identical predictions, that these are just interpretations of what it is that we actually see. So I'm going to just spend a few minutes here and be tutorial. All right, I'm going to derive for you the quantum mechanics of a two-level system, because a two-level system is the exemplar of quantum mechanics. Number one, it's inherently nonlinear, and number two, it really demonstrates all these things all at once, and number three, it's basic to quantum computation. So let's start with the two-slit experiment, okay? And many of you have heard of this, okay? So over here we have a gun. So we have a gun here, and we have a screen with two holes in it, 1 and 2, and we have some kind of a detector over here. We've got a whole line of detectors, actually. And we fire the gun, and if only the first slit is open, okay, only the first slit open, we get a distribution of bullets that looks like this. Everybody good? All right. If only the second slit is open, we get a distribution of bullets that looks like this. Perfectly fine. And if both slits are open, we get a distribution that looks like this, which is the sum of this red line and this green line, okay? And what that is additive probabilities for exclusive events. And this is Laplace, okay? This is standard probability theory that we all know and love. Okay, there we are, okay. Yeah, I just wanted to point out that that's what I have over here, okay? So we've got P1 if 1 is open, P2 if 2 is open, and P1, 2 is just the additive sum. Okay, so what if we do the exact same experiment with water? Well, you all know this, right? Suppose we have a tank of water and we've got two holes in a screen. This is three-dimensional, so we're looking down on this, okay? And we drop a stone or something, and it makes little ripples that go outwards. And if we only open the one thing, we get the red line. If we open only the two thing, we get the green line. But if we open both of them, we get interference. Why do we get interference? All right, the reason we get interference is that the up and down amplitudes from 1 and 2 interfere with each other. So we've got negatives as well as positives coming out of number 1 and out of number 2. Okay, so we write that mathematically like this. So the intensity is the absolute the intensity we observe over here at the screen is the absolute magnitude of something we call the wave function, okay? Because these are waves, right? Okay. And if we open only one, we get phi 1 absolute magnitude squared, psi 2 absolute magnitude squared. But if we open both of them, we add them together before we square the absolute magnitude. And that's where the interference comes from mathematically. Okay, so what if we do this with electrons? Okay, this is an electron gun, but this is a schematic of an electron gun. So we have a piece of metal and we heat it up. That's what the fire is, okay? And the electrons boil off the metal, okay? They come out. For those of you who are physicists, those blue lines are not electric field lines. Those are the paths of the electrons. Anyway, so this is an electron gun, and we put a little another screen with a little round hole in it, and you can see that the electrons then just come out the little hole. Well, that's beautiful. So this, of course, is a cathode ray tube. Okay, so here's the electron gun over here. Everybody knows what a cathode ray tube is, right? It's a TV. Yeah. Okay. It's the kind I have at home. I don't have one of these fancy things. Anyway, so we put a two-slit screen in a TV, and then we measure with a phosphorescent screen or something that happens over there. So what happens? We get interference. All right. So why do we get interference? Don't we think that electrons are sort of like bullets? That is, they're particles. That is, an electron must either go through hole 1 or through hole 2, right? Because electrons are particles. You either have an electron or no electron. You don't have half an electron. This never occurs, right? So why does this happen? We might want to say, okay, let's check. Let's see if we look at the electrons one at a time. We reduce the flux. And if we reduce the flux, we still get interference effects. In other words, the electrons are not interfering with each other. They're interfering with themselves. Okay, in other words, they obey this same mathematics. Okay, okay, you can actually look for the electrons. Okay, you can actually, you know, put a little, what does look mean? It means you put a little light source and you see where they, which slit they come through. Okay, well, if you don't see any of them, you get the wave pattern. If you see them all, you get the particle pattern. If you see some, you get the wave pattern from the ones you don't see, the particle pattern from the ones you do see. But it's worse than this. If we could look, even if we don't look, if we could look after the fact, but we don't, we get the particle pattern. In other words, nature knows. So it's not just that our experiment disturbs the universe. It's that nature knows whether or not we could have looked. Okay, and the most graphic illustration of this, I stole this from Feynman's book, is this one. We've got a scattering of one nucleus A by another nucleus B. So the probability of observing nucleus A at 1, nucleus B at 2, maybe that would be this. So if we've got A and B being two different kinds of nuclei, then we add the probability for observing some nucleus at 1 and some nucleus at 2. But if they're the same nucleus, if they're both, say, alpha particles, we get interference effects, and we actually get double the probability. So this is a measurable effect, okay? I just couldn't resist, and here's my Schrodinger cat state. Okay, this is a very famous thought experiment on the interference of probability amplitudes, but it's also entanglement, okay, the Schrodinger cat state. So you put a cat in a box. This is a cat. This is a very happy cat, but we put it in a box with an amount of radioactive material and a Rube Goldberg device that if the radioactive material emits a particle in a certain amount of time, the vial of poison is broken and the cat dies. So if we wait 1 hour, after which the probability is 1/2 that the radioactive material has actually emitted a particle, and we ask, is the cat alive or dead? And quantum mechanics says yes, the cat is both alive and dead until we look. Okay, and this seems completely unrealistic. By the way, this is not a dead cat. This is a jet-lagged cat. Anyway, so it turns out that we actually have experimental confirmation of this with none other than the buckyballs that I was showing you earlier. Here are the interference patterns by the buckyballs, and these are objects large enough to radiate thermally. But if the photons emitted by a hot buckyball are numerous enough and energetic enough that they carry enough information that could localize its path, even if we don't measure those photons. So this experiment actually shows us that if there's a light inside the box, the cat cannot be in a superposition state, because I could have cut a little window in the box and put it right. And then there's Wigner's friend and everything else. Okay, but let me at least introduce you to path integrals, because this is an extremely graphic way to learn exactly what's going on and to see how quantum mechanics devolves into classical mechanics. And it's a unifying method that can enable us to put in the quantum mechanics in a controlled way. Okay? So we start with the two-slit experiment. We know that the amplitudes for going through slit 1 or slit 2 have to add. That's beautiful, okay? Let's add another couple of slits, okay? And now we have how many possible paths? Well, to be observed over at the final thing over here, hey, there we are, we could have gone through up, 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 or up, down, up, or whatever, okay? So this is now 2 to the 3rd different paths. And then we can double the number, and double the number of slits, and double the number of slits. We can keep on doubling the number of slits until we've got an infinite number of slits. And that's the quantum mechanical path integral, okay? So this is the mathematics for it, in case those of you who are interested. We say that the amplitude for getting over to, say, from the right to the left in a time t is the sum of all possible amplitudes for being on the left, on the right, on the left, right, da, 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 da. All these different strings of possibilities. Left, 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 right, 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 left, you know, all these different possibilities. And we can actually write those as amplitudes, which I'm calling k here, for going in the short time, t over n. So I'm writing this as a product of the amplitudes for going from one place to the other. We can then write an approximate expression for what this amplitude k has to be. If the time t over n is small enough, of course it can't go anywhere. So we just get the identity matrix. If the time t over n is just a little bit larger than that, then we can do a first order term in delta t, and this of course turns out to be the Hamiltonian. And this is the expression for the path integral here. This is in the limit of infinite number of slits. Okay, those of you interested, you can also derive the Schrodinger equation using this. Suppose you have somehow got the amplitude for at time t. Well, then this K matrix here propagates you forward from time t to time t plus delta t. You can just rearrange this, and you recover the Schrodinger equation. You can also recover classical mechanics. How do you recover classical mechanics? Well, the idea with classical mechanics is, of course, as you all know, because you've all done, I'm sure, basic classical mechanics, that given initial conditions, given initial position and momentum of all the particles, you know exactly what's going to happen with the system. This is the trajectory. We all learn in freshman physics how to compute the trajectory given initial conditions. So in the classical limit, this infinity of paths shrinks down to a single path. In the semi-classical limit, you have this semi-classical width of paths on the order of h bar. This actually is where quantum dispersion comes from, okay? So we can see now exactly what quantum mechanics is. Quantum mechanics is the including of an infinite number of other possibilities for how to get from one measurement to the next measurement, and we can include these in our calculations in a systematic way. How do we apply this to temperature, though? I mean, we've heard about this. Okay, so the way the connection is the same operator e to the garbage h, where h is the Hamiltonian. You remember from previous slide that this was the operator e to the iht that propagated us forward in time. Well, if we know a little statistical mechanics, we know that the operator that tells us how a system selects out one of any number of different energy states is with a Boltzmann operator that looks like e to the minus beta h, where here beta is now the inverse temperature in units of Boltzmann's constant. So beta is, if you like, an imaginary time, and we've also heard about this. So we can write something called the partition function as the trace of this operator e to the minus beta h. And the trace, of course, is the sum over the diagonal states. So, for example, in the x basis, that looks like this. And now we can just insert complete sets of states if we write that like this. And now this looks exactly like the quantum mechanical path integral that we saw earlier, except the time is imaginary. So we can discretize, and remember that it's a trace, so that means we have to go all the way around and connect back up where we started from. So that's where this operator came from that you all saw earlier. So again, we've already seen the Hopfield net, so I'll just skip through this. The point is that the Lyapunov function, which we want to minimize in order to find stable states of the net, looks very much like the exponential of this imaginary time path integral that we had earlier. So all we're doing is making a mathematical mapping from the one to the other. And then we can use the machinery of classical neural networks to give us our answer. And we've also seen that before. So we can do a check to make sure that our model works in the classical limit. The classical limit is the limit in which there is no quantum dispersion. So the set of paths, the width of that loop that I was showing you, that actually is a loop over all possible paths that get all the way around, it shrinks down to a single point, and then our results should be comparable to these previously published Monte Carlo results of my friend and colleague Jack Tazinski, and in fact we see something exactly similar. We can do this for a very small network, in which case we get this finite tailing off here, or we can do this for a larger network, in which case we get things going to zero. This is an example of now we're doing actual real quantum processing, okay? So what do I mean by actual real quantum processing? Well, I'm now putting in a finite discretization. That is, I'm not shrinking everything down to a single point for the inverse temperature loop. I'm letting the system explore many different possible states and be in a superposition of states. I still have to integrate over all possible paths, okay, but because I can't integrate over all the infinity of paths. I'm only going to integrate over the finite 2 to the n possible paths that my tiny little computer can handle. So if I start the system out in a superposition state, I actually get quantum coherence along the way. So this shows, and this is a somewhat better picture, that shows, and it's more colorful too, which is always nice. So this shows actual quantum information processing, that we can actually get not just switching from 0 to 1 or from 1 to 0, but switching from a superposition state to another superposition state. These are just representative results. We were able to stabilize these very, very easily. Well, okay, I just want to say one thing about the quantum information processing here, and then I'll do the really new results, and I promise I'll be quiet soon. But in these published results, the temperature, the temperature of the beta loop that we had to use in order to see these quantum mechanical effects was really quite low, 5.8 kelvins. That's very, very low. And of course, your brain is not at 5.8 kelvins. Okay, if it were, you'd be dead. So one asks, okay, do these results actually apply to the real physiological brain? And although this is really a cartoon model, this is a toy model, all right? This includes almost none of the actual interworkings of this extremely complex system that we have, just even in one microtubule, let alone the entire brain, okay? So this is a cartoon model. And we'd think, okay, but if it doesn't work on this cartoon model, how could it possibly work on the larger system? So that's why these calculations were important to do to begin with. But, and on a somewhat more hopeful note, we can also say that the quantum processing here might still work exactly with this temperature. Because why? Because the physiology of the brain may have evolved such that the temperature just in the degrees of freedom of the microtubulins may be that low, okay? When we say temperature as physicists, we mean, well, what is the energy available to that particular degree of freedom? So it might be that while the physiological temperature of the brain is certainly at 36 centigrades. Okay, so this is, and then plus 275 to make it into kelvins. So even though the physiological temperature of the brain is much, much higher than 5.8, the temperature available to these degrees of freedom, to these quantum mechanical degrees of freedom, may be low enough due to screening such that this actually works. We just don't know. Okay, all right, so we've established this model of a microtubule can act as a quantum information processor, but is there any reason to think that it or any quantum neural network can actually do information processing of a sort that a classical computer cannot do? Because if it can't, then we can't possibly get consciousness or anything else interesting. Okay, all we can get is something that we can build in. And that's the most exciting thing. But these are my newest results, and I find them very exciting. I just want to share them with you if you'll be patient for a little while longer. And that's entanglement calculation. A classical computer could never calculate the degree of its own entanglement because it has no entanglement, okay? A classical computer cannot possibly be entangled with anything, okay? Entanglement is a purely quantum mechanical phenomenon. So on a much simpler model, okay, not anything to do with microtubulins, okay, because my computing resources are nowhere near stretched to that, but on a much simpler model, and this is a feed-forward, time-dependent quantum neural network calculation. I have managed to train a very simple quantum neural network. This is now of just 2 qubits to calculate its own degree of entanglement, okay? And by calculate, I mean I didn't just train it to one state and just let it go and say that that's trained. No. I trained it to what neural network people call a training set, and then I tested it on a huge number of other states that it hadn't seen before. And these are some results for the 2-qubit system. Okay, this is my own results, the quantum neural network, which the blue, which essentially overlays the analytic result in gold. If Bennett-Wooters, this is the correct number here. And here are some other calculations. So this shows, for those of you who are up on the physics here, and I'd be happy to answer questions on this for people who are not. This is for a pure state, and this is for a mixed state. And you can see that our quantum neural network, even though it was not trained on any mixed states whatsoever, it was able to reproduce the entanglement for these states as well. Okay, well, that's 2 qubits. how many qubits can you do? All right, so here is some 3-qubit stuff that is shortly to be published. And again, we have some analytic results for something called the 3-tangle. The purple here is the analytic results, and the green is mine. Okay, and you can see again that tracks extremely well. And here we have a 5-qubit system, okay, and for those that we have no analytic results, okay? So I'm able to do even up to 5 qubits. And the really cool thing, guys, and I promise this is my last results slide for those of you who are falling asleep, the really cool thing is the power of interconnectivity, okay? So I just have to show you this. Okay, as you go in stage, and I can explain what the stages are, making the system larger and larger. This is the amount this shows symbolically the amount of training that is needed actually goes down the larger you make the system. So starting out here at the first stage, which was just the 2-qubit system, we got a huge change from an untrained to the trained system. But then as we made the system larger and larger and larger, the amount of change in the parameters of the system actually decreased, which shows you graphically the power of the interconnectivity. The larger you make the neural network, the less training you have to do. Isn't that cool? Okay, well, in conclusions, all right, quantum neural networks can do information processing that neither an algorithmic computer nor a classical neural network can do. Why not a classical neural net? Because a classical neural net can't possibly calculate entanglement. It doesn't know from entanglement, okay? Why not an algorithmic computer? Because we don't have algorithms to calculate the entanglement of a 5-qubit system. But my neural network can do it, okay? Does that mean that a quantum neural network can do consciousness? Well, I don't know, okay? But it can do things that a classical computer can't do, and it can learn things that an algorithmic computer can't do. So the brain may well be a quantum neural network. We need to do a lot more work. So thank you.